Hello! Welcome to Squid Essays. Inking your academic pen. My name is Julie and I will be your instructor as we read through boiling and two-phase flow of mixtures. The article source is embedded in the video description below. Feel free to read along. Please note that you can get a custom, plagiarism-free essay for as little as $10 a page at Squid Essays. The link is in the description. The purpose of this report is to investigate the boiling and two-phase flow of mixtures, particularly for use in cooling and refrigeration applications. A great deal of information is currently available for pure component interactions, however, less information is presented for mixtures. After consulting and reviewing the literature, it was found that many mixture combinations exist capable of replacing pure components. Advantages exist in tailoring the mixture to the application in order to increase safety and overall efficiency and reduce undesirable characteristics. By choosing different properties of the mixture components, greater heat fluxes can be dissipated, thereby increasing the efficiency of the system and reducing requirements such as energy, working fluid volume and surface area. Disadvantages exist in the use of zeotropic mixtures. If zeotropic mixtures are not designed for, then poor operation will occur. This is due to undesirable flow conditions affecting the overall heat transfer of the system and separation of the mixture into a liquid and vapor phase. Composition variations within the working fluid can also cause unexpected operation and must be accounted for. It is seen that some mixtures can be used as drop-in working fluids for existing applications. However, for best results it is more advantageous to design a system with the working fluid in mind from the beginning. This allows maximum efficiency and economic potentials to be met. 1.0 Introduction. The term cooling refers to any process in which thermal energy is transferred via radiation, conduction or convection. There are many processes and applications of this in everyday life, from computing to chemical processes. There is a great understanding of the present technology of heat transfer and of the working fluids involved. However, there are new regions of interest such as micro-applications in computers and applications that require superheat fluxes to be dissipated. Additional interest is in further improvements that could be made to existing processes by altering the operating conditions. Possibly the easiest and most effective change that could be made is to the operating fluid. Differing the fluid changes the properties of the cooling unit. These changes can then be employed to yield more effective results. Changing the fluid may be done for several reasons. To increase efficiency, decrease operating costs, reduce environmental impact and increase safety. Many techniques are currently available to transfer heat. These include air conditioning, air cooling, cryogenics, conduction, solar cells, liquid cooling, refrigeration and thermoelectric cooling. These techniques take place in many different devices, such as heat exchangers, radiators, evaporators, intercoolers, cooling towers and steam generators. The vast majority of heat exchange operations use liquids in order to transfer this heat. This is due to the ease of transporting a liquid through the system compared to a solid, and the heat transfer coefficient being significantly higher than that for a gas. The properties of these working fluids are important in overall efficiency of the process. Many applications use pure components in the cooling system, however the possibilities and range of physical properties are expanded by using a mixture of components. Using different fluids will yield different results and efficiencies. It is important to investigate the advantages and disadvantages of each option. This report aims to investigate the use of mixtures in refrigeration and cooling processes, then assess the advantages and disadvantages of utilizing mixtures in such a role. 2.0 Use of liquid mixtures in cooling applications. 2.1 Refrigeration. A widely used cooling process is refrigeration. The term refrigeration refers to the process of removing heat from a system and transferring it to a region where it has no effect. Refrigeration is used to lower the temperature of the system, and then maintain this decreased temperature. There are three main forms of refrigeration: cyclic refrigeration, non-cyclic refrigeration and thermoelectric refrigeration. Non-cyclic refrigeration does not depend on mechanical work for the process to proceed. The refrigeration depends on a substance changing state by absorbing heat from the surroundings. therefore increasing the temperature of the refrigerant and decreasing the temperature of the surroundings. His method of refrigeration is usually found in short-term applications such as using ice to cool stock at markets or subliming carbon dioxide in a laboratory experiment. Here different mixtures of substances can be used to achieve different overall operations, such as using an ice slurry to reduce the temperature to around 0 Celsius for a period of time. However, by using ice with sodium chloride, the cooling temperature can be decreased to -20 C but for a shorter period of time. Other mixtures include ice and ethylene glycol, propylene glycol, sucrose, glucose and ethanol. This increased cooling effect is due to the melting enthalpy contributing to greater heat absorption than in single-phase coolants. 1. Thermoelectric refrigeration creates a heat flux between two different materials, then transfers heat against the temperature gradient, therefore reducing the temperature of the surroundings. This process requires no working fluid. It is a purely solid-state operation, so will not be included in this report. Cyclic refrigeration is the most common form of refrigeration. It consists of a refrigeration loop where heat is removed from the system and transferred to atmosphere through the use of several working fluids. Two main cycles exist: vapor compression cycle and vapor absorption cycle. Vapor compression cycle operates by compressing the working vapor, then condensed to a liquid, passing this liquid through a throttling valve giving a mixture of liquid and vapor and finally evaporating it. After the evaporation stage, the vapor is passed back into the compressor for the cycle to start again. Vapor compression is the most widely used refrigeration method. It is used in large and small-scale processes, in domestic and industrial applications. These processes include air conditioning units in buildings and cars, refrigerators and freezers, some cooling of electronics, chemical separators and liquefaction processes. Vapor absorption refrigeration has a comparable cycle to the compression cycle, except from the process of increasing the pressure of the working vapor. The absorption system contains an absorber which dissolves the refrigerant into a liquid, then a pump raises the pressure and a generator removes the refrigerant vapor from the high-pressure liquid. Work is required by the liquid pump, however it is much smaller than required by the compressor in the vapor compression cycle. It is important to operate suitable combinations of refrigerants and absorbents in order to maximize efficiency. There are a wide range of applications for cooling fluids and refrigerants in which there is large interest: air conditioning units in buildings and cars, refrigerators and freezers, cooling of electronics, nuclear reactor cooling, cooling streams on many chemical plants, separators, liquefaction processes. Many of these applications use substances that are rapidly becoming unfavorable, such as chlorofluorocarbons, CFCs, which are being phased out and will be totally replaced by 2020 in developed nations. The widely used interim replacement for CFCs are hydrochlorofluorocarbons, HCFCs, due to their reduced ozone depletion potential, typically 1 to 10% that of CFCs, and hydrofluorocarbons, HFCs, due to their 0% ozone depletion potential. However, there are significant drawbacks in using these as replacements. HCFCs cannot be considered long-term alternatives as they still contribute to ozone depletion and are expensive. Despite having no impact on the ozone, HFCs are not ideal for long-term use as they are more expensive than CFCs, are difficult to work with, offer reduced performance and have a short lifespan too. To regain some of the favorable properties that CFCs add, mixtures of components are being studied to see whether a compromise of two or more refrigerants can give similar results to that of chlorofluorocarbons. It would be particularly beneficial if a mixture could be formed for use in an existing refrigeration system, as this would mean only the working fluid would need to be replaced, leaving the existing mechanical process untouched. Dichlorotafluoromethane, R12, was used extensively in domestic refrigerators. However, since its ban in 1994, mixtures of hydrocarbons and hydrofluorocarbons have been investigated as possible replacements. One possible mixture is that of propane, butane and 1,1,1,2-tetrafluoroethane, R134A. Experimental research shows that ternary mixtures of butane-propane R134 can be just as successful for domestic refrigeration as R12. A number of tests have been performed at a range of evaporator duties, 100 to 350 W, in a domestic refrigerator whilst varying the composition of the refrigerating mixture in between trials. It was found that a mixture of propane-butane R134 with mass fractions of 31.25 over 31.25 over 37.5% could successfully be installed in a domestic refrigerator originally designed to work with R12, without modifying any part of the refrigeration apparatus. This mixture gives performance characteristics very similar to those of R12. The coefficient of performance at a 100 W evaporator duty is 5.4% less than that of R12, and 0.8% less at a 350 W duty 3. These differences are due to the slightly higher compression power requirements of the mixture but are negligible when considering a relatively small refrigeration unit. An increased volumetric efficiency for the compressor is also noticed when operating with this mixture. Applying this mixture to larger scale operations is not possible. 3. As the larger the evaporator duty becomes, the further the coefficient of performance deviates from the initial refrigerant, causing severe efficiency losses on industrial scale applications. The majority of HFCs have high global warming potentials, GWP. This means that although they do not deplete the ozone, they do contribute to global warming and therefore cannot be considered for long-term use. As hydrocarbons are an environmentally acceptable alternative and inexpensive, their use as a refrigerant in domestic refrigerators is very attractive. Mixtures of hydrocarbons are presently being used as a replacement for both CFCs and HFCs. Recent experiments have been conducted using LPG, 30% propane, 55% N-butane and 15% isobutene by mass. These experiments have concluded that by altering the masses of refrigerant, an optimum working mass can be found. For LPG, it was found that a mass of 80 G/100 W evaporator duty gives the best performance relative to R12 and R134A. However, if the number of components present is reduced to 2, then the refrigerator operating with propane-butane, 60% per 40% by mass, needs less external energy to be supplied compared with a refrigerator operating with propane-isobutane, 60% per 40% by mass. This is due to the latency to the propane-butane mix being higher than that of the propane-isobutane. Therefore, the mass of propane-butane is lower than that of the propane-isobutane at 70 G/100 W and 75 G/100 W respectively. 4. This means the duty of the compressor is reduced, leading to reduced overall energy consumptions, while still transferring the same heat duty as the other mixtures. Aside from the mixtures used, the flow boiling heat transfer of mixtures has a large influence on the success of the techniques being used. 5. Extensive experimental results show that when using mixtures as the working fluid, a direct comparison with pure components is difficult due to the effects of mass diffusion between the components in the mixture. 6. 7. Experiments of flow boiling with a mixture of bromotetrafluoroethane/diflavor 1,1-ethane, R13B1 per Raumur 152A, in a horizontal tube have shown that local and average heat transfer coefficients for the mixture are significantly lower than for either pure component 8. Further work has shown that with the R13B1 per Raumur 152, a mixture having composition of 0.07, 0.22, 0.36 and 0.64 mole fraction R13B1, there is a substantial loss of heat transfer coefficient with increasing R13B1 mole fraction. However, the most unusual trend found during this experiment was that a circumferential variation of wall temperatures was noticed with mixtures in an annular flow regime. During annular flow, heat is conducted across the liquid layer. The liquid film at the bottom is thicker than that at the top due to gravity. As a result, for pure components, the wall temperature at the bottom of the tube was higher than at the top because of the increased resistance to heat transfer conduction, resulting in a lower heat transfer coefficient at the bottom of the tube. For mixtures, new traits were observed. Wall temperature at the bottom of the tube was lower than the top. This behavior is expected to arise from composition variations around the circumference of the tube. Heat transfer coefficients for mixtures were constant over the composition range of 0.1-0.64 mole fraction of R13B19. However, large discrepancies were seen in the locations of heat transfer. Further studies of flow boiling heat transfer have enlightened new characteristics of pure refrigerants and a non-azeotropic refrigerant mixture in horizontal tubes. A series of tests were carried out for pure and mixed refrigerants of chlorotafluoroethane, R22, and 1,2-dichlorotetrafluoroethane E, R114, at different compositions. Results found that nucleate boiling was totally removed for mixed refrigerants and most heat transfer occurred during the convective evaporation region. In this region, heat transfer coefficients of mixtures were almost 36% lower than the expected ideal values. Variations of wall temperature when using mixtures arose from composition variations of up to 0.07 mole fraction between the top and bottom of the tube, causing the corresponding circumferential variations 9. In addition, flow patterns change with composition, leading to uneven heat transfer 10. Flow boiling of pure refrigerants and refrigerant mixtures in horizontal tubes have also been investigated. Mixtures of difluoroethane/tetrafluoroethane, R32 per Rayamir 134A, propane isobutene, R290 per Rayamir 600A, non-azeotropic refrigerant mixtures, and difluoroethane/pentafluoroethane, R32 per Rayamir 125, azeotropic refrigerant mixture, were used as the working fluids. These mixtures have zero ozone depletion potential and are used to replace CFCs and HCFCs. It was concluded that heat transfer coefficients depend strongly on heat flux in the laminar flow rate region 11. Boiling of mixtures differs substantially from that of pure fluids due to a number of factors such as the effect of composition on nucleation 12, significant changes in physical properties of mixtures with composition 13, and the reduction of vapor-liquid exchange and evaporative mechanisms 14. The heat transfer coefficient of mixtures is generally lower than that of the equivalent pure fluid with the same physical properties. Theoretical models suggest that the mixture affects nucleate boiling and the thermal resistance in the vapor phase, therefore causing a decreased heat transfer coefficient. Using mixtures of refrigerants causes the heat transfer coefficient of the mixture to be significantly lower than that of pure fluid in the boiling dominant region, but is almost equal in the convection dominant region. This is due to the effect of diffusive resistance being small in the convection dominant region 15. 2.2 Micro applications. In recent years there have been many technological advances in the microelectronics industry. This has led to an increase in density and speed of electronic chips and therefore an increase of dissipated heat flux. New high-powered electronic chips can potentially generate heat fluxes of up to 100 watts per centimeter too. As existing cooling systems cannot dissipate this flux effectively, there is a buildup of temperature within the electronic device and premature device failure can occur along with compromised safety. It has been proposed to cool the electronic chip with a liquid mixture in order to dissipate this heat more efficiently. Therefore it is important to understand the boiling and two-phase flow of mixtures in small-scale systems. Many advanced technology and traditional industries such as electronic, pharmaceutical and medical industries are also increasing their dependence on micro-scale thermal, fluid and chemical systems for increased quality of product and increased efficiency of the process. For example, applications of compact evaporators in hydrocarbon separation, liquefaction of gas, nitrogen, helium, natural gas, and the separation of oxygen and nitrogen. This means total re-engineering of the process is required, including micropumps, compressors, turbines and heat exchangers, as well as the working fluid within the cooling systems. Although this technology is still young, much research has already been carried out. Now particular areas of interest are in understanding flow patterns on small-scale applications, flow boiling heat transfer, critical heat flux, CHF, and two-phase flow pressure drop. Significant differences of transport phenomena between small diameter channels and normal size channels exist, so it is important to distinguish between them to prevent confusion. A unanimous agreement has not been established yet, so for the basis of this report the hydraulic diameter will be used to define the category of scale. The transition between small and normal sized channels will occur at a hydraulic diameter of around 7 mm. The most common two-phase flow and flow boiling of mixtures application is within capillary tubes and refrigeration, heat pump and air conditioning systems. A capillary tube is a constant area expansion device used in small-scale systems. This tube usually has an inner diameter of between 0.5 to 2 mm and a length ranging from 400 to 2500 mm. A vast quantity of data for an adiabatic capillary tube with use of CFC and HFCs has been compiled. However, a search for alternative refrigerants has become an important region of investigation. Refrigerant mixtures have been chosen to replace these unwanted refrigerants in small-scale applications. Engineers now must research the performance of capillary tubes using alternative refrigerant mixtures in order to correctly design new refrigeration equipment. This will include determining appropriate length and diameter of the capillary tubes at given refrigeration capacities and operation conditions. It is, therefore, required to understand the process of gas-liquid two-phase flow and flow boiling of new refrigerant mixtures in capillary tubes. Limited study has been reported under these conditions, although there are a lot of studies of two-phase flow and flow boiling of pure fluids in small and mini channels. One possible reason for this is due to the complexity and difficulty of studying the two-phase flow and flow boiling phenomena of mixtures in small and mini channels. The research that is present includes two-phase flow frictional pressure drops, mass flow rates, qualities and temperatures. Experimental and theoretical models have been created to provide a basis for the design and operation of capillary tubes and working systems. Experiments of flow boiling using water-methanol binary mixtures in horizontal microchannels with hydraulic diameter between 0.133 to 0.343 mm have investigated the influence of liquid compositions of the more volatile liquid on the heat transfer performance, and the flow boiling phenomena in the microchannels were of particular interest. These experiments found that during the boiling of binary mixtures, as the component concentrations in the liquid and vapor phase change along the test section, the local bubble point temperature rises as a heavy component builds up the liquid phase 16. Thus not only must latent heat be added to the fluid to evaporate it, but also sensible heat must be added to both phases to heat them up to the new local bubble point temperature 17. Studies of flow boiling of mixtures in plate heat exchangers with small hydraulic diameter channels have also been presented. Boiling heat transfer and frictional pressure drop of the mixture of difluoroethane, R32, and pentafluoroethane, R410A, in a heat exchanger with a hydraulic diameter of 6.6 mm were examined. It was found that both boiling heat transfer coefficient and frictional pressure drop increased linearly with heat flux. In addition, the refrigerant mass flux has significant effect on the flow boiling heat transfer coefficient at high heat flux. It was also noted that refrigerant pressure has very slight influence on the heat transfer coefficient 18. With the progress of new technologies related to this area, there is an incentive to further research two-phase flow and flow boiling of mixtures in small and mini channels. For both theory and practical uses, current deficiencies in knowledge could be recovered by exploring two-phase flow and flow boiling of mixtures over a wide range of channel diameters in the microscale. Investigating the effect of mixture composition on heat transfer coefficient and two-phase pressure drop. Flow patterns and transition regions of two-phase flow and flow boiling of mixtures in microchannels. 15.3.0 Azeotropic, near-azeotropic and zeotropic mixtures. Azeotropic mixtures are mixtures that behave like a pure fluid, that is, under constant pressure they will condense or evaporate at a constant temperature and the composition in the vapor and liquid phases will remain the same. This means that any refrigerant leak from the system will not change the composition of the remaining refrigerant, meaning that the refrigeration system will continue to operate as normal. Figure 1 shows that at the azeotrope point there is only one possible composition of the mixture at corresponding pressure. The composition at which an azeotropic mixture exists is a function of temperature, therefore no azeotropic mixtures can fully exist in refrigeration 21. However, the azeotropic mixtures used to have a very small composition range, therefore can be treated in the same way as a true azeotrope. Successful use of azeotropic mixtures has led to wide use in refrigeration. Near-azeotropic mixtures are mixtures that have small temperature variations during phase change, and little difference in composition in the vapor and liquid phases at equilibrium. Due to this fact, use of near-azeotropic mixtures have only been used to give a wider range of refrigeration possibilities. Their use is not ideally suited to cooling and refrigeration applications. 19. An example of this is the addition of small amount of propane to R502 to increase its solubility in the lubricating oil. 21. Non-azeotropic, zeotropic mixtures have different vapor and liquid compositions when in equilibrium. From Figure 1 it can be seen that there is a wide range of possible compositions between the dew and bubble point curves, to the left and right of the azeotrope point. This is the result of non-similar boiling points of the individual components that make up the zeotropic mixture 20. During phase change, different boiling points of the individual components leads to different evaporation or condensation temperatures relative to the other components. This leads to a change in the composition of the mixture, therefore changing the dew and bubble point temperatures of the remaining mixture 21. 4.0 Flow characteristics. 4.1 Temperature glide. A non-isothermal phase change process occurs within the dew and bubble point temperatures known as the temperature glide. The magnitude of this temperature glide is dependent on the boiling points of the components and the composition of the mixture. Temperature glide decreases with increasing pressure. Mixtures with significant temperature glide, greater than 5 Celsius, in theory have the potential to improve performance and energy efficiency of vapor compression systems. 21. In order for these improvements to take place, the temperature profiles of the refrigerant and the heat transfer fluid must be coordinated. This allows a fairly constant, small temperature difference between the two different streams. This process is known as glide matching. It reduces the possibility of reverse heat transfer, thereby improving the performance and energy efficiency. Temperature glide matching can be analyzed by interpolating from the temperature entropy graph for the refrigerant. Perfect glide matching is only achievable in some heat exchanger setups. Possible configurations include shell and tube, annular tubes and flat plate heat exchangers. It is not possible to match the temperatures in micro heat exchangers as they do not fully comply to counterflow conditions. Advantages of glide matching are: I. The compressor will be operating under a reduced pressure range, improving performance. E. Higher stream temperatures can be achieved using appropriate mixtures, using less compressor work. 21. To have a successful temperature glide match, an adequately sized heat exchanger is needed. Smaller temperature differences require larger heat transfer areas to transfer the same heat capacity. The right combination of heat exchanger size, heat transfer fluid and refrigerant contribute significantly to the actual performance of temperature glide matching. If the cooling system requires use of a linear refrigerant and a heat transfer fluid, glide matching can only be achieved by altering the heat transfer fluid flow rate. 22. Looking at Figure 2, a large gradient represents a higher mismatch in glides that leads to poor performance. 4.2 Circulating composition. When a single component is used in a vapor compression system, the concentration of the refrigerant throughout the system is equal. However, when zeotropes are being used, composition variations are noticed. 23, 24. This difference is thought to arise from internal fractionation of zeotropes. 24. Fractionation is the result of preferential boiling, or condensation, in the mixture components. During the boiling process, the vapor phase gains the more volatile component from the mixture while the liquid phase loses this component. This causes the less volatile components to be held up, causing the mixture composition within the system to become different than that of the original. This shift in circulating composition leads to altered system pressures, temperatures, capacity and energy efficiency. 25, 21. 4.3 Condensation. The condensation heat transfer phenomenon for mixtures is fairly complex. Investigations into the effect of mixture composition on heat transfer coefficient have not shown any recognizable pattern. 26. However, it is known that stratification of the composition and the temperature in the vapor phase reduces the heat transfer coefficient. 27. The effects of stratification decrease as vapor velocity increases. During condensation, the low volatility components diffuse into the vapor away from the vapor-liquid interface. This mass fraction gradient causes a thermal gradient and mass transfer resistance in the vapor diffusion layer, affecting the condensation. This influence depends on the volatility difference between the mixture components. Furthermore, in forced convection, the composition of the mixture, the shape of the surface and the velocity of the vapor influence the heat transfer coefficient significantly. 21. 4.4 Boiling and evaporation. Using more than one component for mixture refrigerants changes the required superheat to initiate and sustain nucleation. 12. The change in superheat is the foremost and most complex contributor to the heat transfer coefficient depletion of mixtures. 28. Bubble growth during nucleation is limited by the liquid bordering the bubble surface becoming enriched with the more volatile component. For a binary mixture, the minimum heat flux increases with the presence of an additional component. This shows that more heat transfer and a larger wall superheat are required to initiate the boiling process. 22. These cause considerable reduction in nucleate boiling heat transfer. The heat transfer coefficient of nucleate boiling is much lower than that of a pure refrigerant with similar physical properties. This decrease in heat transfer coefficient increases with pressure and does not change with composition. 29. The heat transfer coefficient deterioration is mainly due to a rise in the local boiling point temperature due to evaporation of one of the components during bubble formation and growth. 30. In addition, the mass transfer resistance resulting from concentration difference between the vapor and liquid phases aggravates the heat transfer deterioration. 31. As with pool boiling, forced convective heat transfer of mixtures is fairly poor. It is thought that the mixture heat transfer coefficient is a function of the overall composition, and the physical properties account for about 80% of the heat transfer reduction seen in mixtures. In addition, the effect of mass flux has a large influence on the heat transfer coefficient due to changes in mass transfer resistances caused by depletion of the more volatile components. 21. 4.5 void fraction. The most significant variable in two-phase flow and heat transfer is the void fraction of the vapor phase in the cross-section of the flow channel. The void fraction is regarded as the volume lost to the vapor phase within a system. Four main vapor flow regimes exist: bubble, slug, annular and stratified flow. Under bubble flow the majority of the working fluid is liquid, however small bubbles form and flow at a roughly equal flow rate to the vapor phase. This regime does not have a significant impact on the overall efficiency of the system, however it can cause problems for the hardware that is pumps. Slug flow has a larger vapor phase within the tube. As the two phases move at different flow rates, uneven flow occurs as seen in Figure 3. Annular flow has the majority of the vapor phase traveling in the center of the tube and liquid on the walls of the tube. This regime requires a large vapor flow rate and can have very significant effects on both efficiency and the system operation. Stratified flow has roughly constant low flow rates for both liquid and vapor phases, which causes the flow to separate into two distinct laminar flows as seen in Figure 3. Stratified flows are most common in the cooling processes, however they are just as undesirable as annular flow. As the vapor and liquid phases do not travel at the same velocity, the void fraction and dynamics of the two-phase interface are a function of the flow itself. 32. This void fraction decreases the heat transfer coefficient, leading to decreased overall efficiency. Void fraction is a much larger problem in micro applications as the vapor bubbles formed usually lead to slug flow, which can decrease the efficiency by up to 40%. 32. 4.6 flow patterns during practical applications. Major design complexities arise when dealing with two-phase flow. Mass, momentum, and energy transfer rates are quite sensitive to the geometric distribution of the system. Geometry can strongly affect the interfacial area available for mass, momentum or energy transfer between phases. Different flow patterns mainly occur as a result of geometry, volume flow and components in the mixture. The boundaries between these flow patterns occur because one flow regime becomes unstable as the boundary is approached. This instability increases and causes transition to another flow pattern. 33. These phase transitions are unpredictable as they depend on many other variables of the flow. This means that flow pattern boundaries are never distinguished lines but poorly defined transition zones. Figure 4 shows the rough boundary regions of two-phase flow for a water-air mixture. Marked on the diagram are flow regions that is low liquid mass flow rate and high vapor flow rate would lead to wave flow, or high flow rates of both liquid and vapor would lead to slug verging on annular flow. The hatched regions are practical regime boundaries and solid lines are theoretical predictions for phase boundaries. Many different forms of this chart exist, and will change for flow rates and for component mixture. 5.0 Advantages of using mixtures. Mixtures offer the advantage of tailoring the composition to suit various temperature requirements of the system. By choosing a mixture with suitable characteristics for the application, greater heat fluxes can be dissipated, smaller units can be installed and therefore greater overall efficiencies will be noticed. It is also possible to control the properties such as toxicity, flammability, oil miscibility by manipulating the composition. If a zeotropic mixture is chosen, then vapor compression cycles can be improved by choosing a suitable temperature glide. Hence, mixtures are finding greater use. 6.0 Disadvantages of using mixtures. The advantages brought forward with mixture use also bring forth several disadvantages. If a leak occurs within a system, the composition of zeotropic mixtures will be changed, thus changing the way the cooling or refrigeration system operates, therefore reducing efficiency. If the heat duty of the application causes only one component in the mixture to evaporate, then the efficiency of the whole system will be disturbed. This is due to the heat transfer coefficient of the vapor being less than the liquid and therefore causing uneven fluid flow. A further consequence of evaporation or boiling in the system will be that of increased pressure. If the system is closed, this will have safety consequences as well as operational consequences. Flammable refrigerants are gaining increased use, and it is believed that servicing of such systems is a potential safety hazard. It is therefore necessary to educate the operators in the correct maintenance procedures. 7.0 Conclusion. The most effective substances used as the individual components in a cooling mixture are readily available in pure form, stable, non-hygroscopic and non-aggressive. This means that once combined to form the operating working fluid mixture, the components will not react with any other substance they may come in contact with and will not attract water molecules from the surroundings. These characteristics ensure a fairly predictable operating system and one which can be operated for prolonged periods of time without excessive maintenance. It is also important to ensure that the azeotropic mixture composition should change very slightly with temperature if temperature glide has not been accounted for in the design stage of the cooling system. The defining characteristic of a minimal temperature glide is that the molar evaporation heats of the individual pure substances forming the azeotropic mixture will be of similar magnitude. The relative independence of the vapor composition from temperature in the azeotropic mixture is very important and must be considered before using as the working fluid. In order to assess the level of independence, gas chromatographic procedures should be used. Concentration of the vapor phase at equilibrium should be calculated at various temperatures in the azeotropic mixture. 36. For large and normal scale operations, it is particularly beneficial to utilize mixtures in place of pure components, as this allows for greater operating efficiencies to be found. It is also possible to model the whole system in practical and theoretical terms as the process is fully understood. As for small diameter channels, no correlation and heat transfer mechanisms are available. Even for the experimental studies of flow boiling, heat transfer available in the literature, two main limits exist. Firstly, some data reduction methods are not appropriate. The other is that there are limited test channel diameter range for both small and micro dimensions. 15. In all, there lacks a systematic knowledge of two-phase flow and flow boiling of mixtures in small and mini channels. However, it is still a long-term task to achieve an understanding in this important area because of the complexity and difficulty of two-phase flow and flow boiling phenomena of mixtures in small and mini channels. Efforts should be made to contribute to both experimental and theoretical studies in this important area in the future. 8.0 References 1. Guobang Chen, Zhehuagan, G. Thumbs, C. Hutton, 2000. Thermodynamic Performance Prediction of Pulse Tube Refrigeration with Mixture Fluids. Cryogenics 40, 2000, 261-267. 2. Jianyang Chen, Jianlin Yu, 2008. Performance of a new refrigeration cycle using refrigerant mixture R32 per Rayamir 134 for residential air conditioner applications. Elsevier Energy and Buildings 40, 2008, 2022-2027. 3. B-Tashtush, M-Tad, A9AYTZ2XZ6, 2002. Experimental study of new refrigerant mixtures to replace R12 in domestic refrigerators. Applied Thermal Engineering 22, 2002, 495-506. 4. A9AYTZ2XZ6, 2005. Experimental study of hydrocarbon mixtures to replace HFC 134 in a domestic refrigerator. Energy Conversion and Management 46, 2005, 85-100. 5. John W. Coleman, Srinivas Garamella, 1998. Characterization of two-phase flow patterns in small diameter round and rectangular tubes. International Journal of Heat and Mass Transfer 42, 1999, 2869–2881. 6. Stephan, K., 1995. Two-phase heat exchange for new refrigerants and their mixtures. Int. J. Refrigeration 18, 198–209. 7. Steiner, D., Taborek, J., 1992. Flow boiling heat transfer in vertical tubes correlated by an asymptotic model. Heat transfer Eng 12, 43–69. Rademacher, R., Ross, H., Didion, D., 1983. Experimental determination of forced convective evaporative heat transfer coefficients for non-azeotropic refrigerant mixtures. ASME National Heat Transfer Conference, ASME 83, WAHT54. 9. Ross, H., Rademacher, R., D. Marzo, M., Didion, D., 1987. Horizontal flow boiling of pure and mixed refrigerants. Int. J. Heat mass transfer 30, 979–992. 10. Shin, J.Y., Kim, M.S., Rowe, S.T., 1997. Experimental study on forced convective boiling heat transfer of pure refrigerants and refrigerant mixtures in a horizontal tube. Int. J. Refrigeration 20, 267–275. 11. Boisiu, X., Heigl, M.R., Jens, R.A., 2000. Two-phase heat transfer coefficients of 3 HFC refrigerants inside a horizontal smooth tube, Part I, evaporation. Int. J. Refrigeration 23, 269–283. 12. Schock, R.A.W., 1977. Nucleate boiling in binary mixtures. Int. J. Heat mass transfer 20, 701–709. 13. Stephan, K., Poiser, P., 1979. Heat transfer and critical heat flux in pool boiling of binary and ternary mixtures. Jur. Chem. Ang 2, 161–169. 14. Thom, J.R., 1982. Latent and sensible heat transfer rates in the boiling of binary mixtures. J. Heat transfer 104, 474–478. 15. Lixin Cheng, Dieter Muse, 2006. Review of two-phase flow and flow boiling of mixtures in small and mini channels. International Journal of Multiphase Flow 32, 2006, 183–07. 16. Peng, X.F., Wang, B.X., 1998. Force convection and boiling characteristics in microcanals. In Proceedings of 11th IHTC, 23–28 August 1998, Gyeongju, Korea, Volume 1, pages 371–390. 17. Peng, X.F., Peterson, G.P., Wang, B.X., 1996. Flow boiling of binary mixtures in microcanaled plates. Int. J. Heat mass transfer 39, 1257–1264. 18. Shi, Y.Y., Lin, T.F., 2002. Saturated flow boiling heat transfer and pressure drop of refrigerant R410A in a vertical plate heat exchanger. Int. J. Heat mass transfer 45, 1033–1044. 19. Didion Da, Bivens D.V. The role of refrigerant mixtures as alternatives, in Proceedings of the ASHRAECFC Technoconf, NIST, Maryland, 1989. Pages 57–69. 20. Stewart C.F., Murphy T., Wilkinson S. Composition shifts of zeotropic HFC refrigerants in service. ASHRAE Trans 1994. 100, Part 1, 538–46. 21. Leelananda Rajapaksha, 2007. Influence of special attributes of zeotropic refrigerant mixtures on design and operation of vapor compression refrigeration and heat pump systems. Energy Conversion and Management 48, 2007, 539 to 545. 22. Rajapaksha Al Performance Evaluation of Reversible Heat Pumps when Using Refrigerant Mixtures, PhD Thesis, University of London, 2003. 23. Cruz H., Coover M., Quastu, Schroeder M., Upmeyer B. Theoretical and Experimental Investigations of Advantageous Refrigerant Mixture Applications. ASHRAE Trans 1985. 91. Part 2B, 1383-418. 24. Cruz H., Wieskalic F. Concentration Shift when Using Refrigerant Mixtures. ASHRAE Trans 1997. 103. Part 1, 747-5525. Chen J., Cruz H. Calculating Circulation Concentration of Zeotropic Refrigerant Mixtures. HVACR Rays 1995. 1, 3, 219-31. 26. Tandon TN, Varma HK, Gupta Camp. Generalized correlation for condensation of binary mixtures inside a horizontal tube. J. Refrick 1986. 9134-6. 27. Wang S., Chato J.C. Review of recent research on heat transfer with mixtures, Part 1, Condensation, Part 2, Boiling and Evaporation. ASHRAE Trans 1995. 101, Part 1, 1376-401. 28. Collier J.G., Foam Junior Convective Boiling and Condensation. 3rd ed. Oxford, Clarendon Press. 1996. 29. Foam Junior Boiling of New Refrigerants, a State-of-the-Art Review. J. Refrick 1996. 19. 7. 435-57. 30. Schlunder EU. Heat Transfer Studious Nucleate Boiling of Mixtures, in 8th and Heat Transfer Conf, San Francisco, 1986. 4073-2079. 31. Alpha-HE, Balkan F. Nucleate Pool Boiling Performance of Acetone Ethanol and Methylene Chloride Ethanol Binary Mixtures. J. Heat Mass Transfer 1989. 32. 12. 2403-8. 32. Wolverine Tube, Incorporated 2009. Engineering Data Book 3. Chapter 17, Void Fractions in Two-Phase Flow. 33. Brennan, Christopher Earls, 2005. Fundamentals of Multiphase Flow. Cambridge University Press. 34. Russo, Ronald W. James R. Fair, 1987. Handbook of Separation Process Technology. Wiley IEEE. Pages 261 to 262. 35. Nakakachurl, Luki K. Cheney, 1997. The Optimal Design of Refrigerant Mixtures for a Two-Evaporator Refrigeration System. Department of Chemical Engineering, U222. PS 0098-1354, 97, 0073-2. 36. BVIF, A.G. Wittenberg, A.N. Marinichev, U.M. Kuznetsova. Application of azeotropic mixtures as standards in testing gas chromatographic systems and components. Chromatographia, Volume 9, Number 10, October 1976. Please be aware that the free essay that you were just reading was not written by us. This essay, and all of the others available to view on the website, were provided to us by students in exchange for services that we offer. This relationship helps our students to get an even better deal while also contributing to the biggest free essay resource in the UK. Thank you for taking your time to listen to me. I hope you enjoyed learning about boiling and two-phase flow of mixtures as much as I did. Kindly remember that you can get a custom, plagiarism-free essay at Squid Essays for as little as $10. The link is in the description. See you next time.